most of our metabolic pathways last time. But what I always like to do, I kind of say it all to you once, and then I kind of quickly go back through it, and hopefully when you hear it the second time, it just flows right together. We still have not finished photosynthesis. I know there's one more part of photosynthesis we didn't do at all. So I'm going to go back through everything we've already done a little quicker, and then when we get to photosynthesis, I'll slow back down and point things out. This is your chance to ask questions and make sure everything in these pathways makes sense. But as we go through the pathways, what are we focusing on? Are we focusing on memorizing what steps occur? The overall goal. Why did we do this? Okay? So that's what we need to focus on. When you take a test, that's what I'm going to focus on. I'm not ever going to ask you specific details about what molecule is converted into another molecule. It's going to be overall goal. Where is the energy made? Where is the NADH made? You know, important steps like that. Okay? So if we start with our first step in carbohydrate catabolism, we need to go back through glycolysis. In glycolysis, we take a molecule of glucose and split it into half, forming 2 molecules of pyruvate. Make a little bit of energy and a little bit of NADH. What is the purpose of glycolysis? To make a smaller molecule out of your carbohydrate. Why is the purpose not to make energy? Why is making energy not the purpose? It makes a very, very tiny amount. And if the organism has the ability, he does not want to have to live off of that little bit of energy. So he's simply trying to make that giant sugar smaller. Why is he making it smaller? So it can go into the next set of steps and be made even smaller. Well, to give you guys kind of a hint, if you can at least learn the order, it goes glycolysis, Krebs, etc., the end product of the one cycle is always being made for the next cycle. So we're making this smaller in glycolysis so that smaller molecule can go to the Krebs cycle, so it can move on into the next cycle. Is everybody good with that? Okay. Now we have Krebs cycle. Step 1, we take pyruvate, break it down into acetyl-CoA. All right. What are we doing in that little intermediate or bridge step? Okay, let me ask you a different way. Why are we releasing carbon dioxide as a waste product right there? What did we do? Come on, we took it from 3 carbons into, we made it smaller again, right? We went from 3 carbons to 2 carbons. The reason we have that CO2 waste product is because we're still chopping carbons off, and we got to have a way to get rid of them. In glycolysis, we didn't just chop off carbons and throw them away, right? We did an exact splitting of the sugar in half. Now, as we go to try to make it smaller, we can't split it in half anymore, right? It's 3. You can't split 3 carbons equally in half. So now we're just to the point where we're having to chop carbons off. And that's why you start getting that carbon dioxide as a waste product. Okay? Y'all stop me at any point if something doesn't make sense. Now we go into the Krebs cycle. In the Krebs cycle, you have a molecule combined with acetyl-CoA. You go through the cycle, and you make the original molecule again. What is the purpose of the Krebs cycle? Why do we want to keep it going? Forming NADH. What does NADH do for us? Carries what? Electrons. Why do we need to get electrons? What is the next step we're going to go into? Electron transport chain. So the purpose of the Krebs cycle is to get our electrons out of our molecules so our electrons can go into the electron transport chain. Make sense? Okay. Good. That's the goal. Well, if you're talking product and substrate for Krebs, you're going to have several at each different step. The initial substrate would be acetyl-CoA and oxaloacetic acid. So that would be your initial substrate. Goes in, then you go through several steps. your eventual product is oxaloacetic acid again. What you actually start with is what you make. That's what makes it a cycle. Okay. All right. So now we've gotten our electrons. We're ready to go to the electron transport chain. And this, I agree, is the more complex steps in all of these pathways. But once we learn it once, we just use it over and over and over again. So, okay, it's bad, but we got to learn it once. What is the overall purpose of the electron transport chain? Making energy, right? So we split it in half. We got our electrons out. Now we're finally going to make energy. Okay, just going step by step. Now, how do we make that energy? First, we've got to give an electron to our first protein. Where'd the electron come from? NADH, that we just made in the Krebs cycle. Okay, so we're just following step by step. Electron starts hopping from protein to protein. Every time that electron jumps, what happens? We move protons from one side of the membrane to the other. Now we've got a whole bunch of protons on the top, right? If we have more molecules on one side of the membrane than the other, they're naturally going to want to move, right? If you put any molecule and you separate them by a membrane, wherever you have more of them, you now have a concentration gradient. So in this picture, the way we have it drawn, we have a concentration gradient of protons on the top. Since there's more on the top, they naturally want to flow down through this last protein. What's the name of this protein? ATPase, ATP synthase, same thing. As those protons flow through, what happens? It starts spinning, and we make our energy. Okay, you don't have to know all the details. I know I did my beautiful ballerina turn. But what's important is that you understand it. That's how we're making the energy. All right, a few important questions. What's the purpose of oxygen? The purpose is not to make water. You do make water, but what's the purpose? To grab that extra electron, right? We said we gave the electron to number 1, and that electron started hopping. But when we're done with the electron, it can't just float around our body. So the electron combines with oxygen, makes water. Okay? Electrons are bad for us, water's not. Just turning it into something that will not hurt us. Okay? So do we feel any better about it now as we see it kind of flowing through? A little bit better? Okay? The more you do this, the better. Now, I did not require you to use your access code that should have come with your textbook for masteringmicrobiology.com, but there's information in the front of your textbook on how to log into that website. Some of your teachers may have used that for biology or A&P. There is one for micro. If you want, you can go to that website and listen to them, somebody else's voice, explain these cycles to you. If you don't want to bother logging into that, you can get on YouTube and just type in the cycles, and you can watch different people explaining the cycles to you. But always be a little leery when you listen on YouTube because it may not be right, So just, make sure you're listening to a good source. The more you hear it, the better. Believe it or not, I explained it in a very simplistic way. So if they start throwing out words that confuse you, just don't listen to it. Find another one. Okay? Our goal is overall purpose of each step. Go ahead. It may not be a code. It may just be instructions on how to get to it. I can't remember what's exactly in your book. But you have access to it with your textbook. Okay? All right. So now we can think about the alternative that some organisms have to doing that glycolysis, Krebs, and electron transport chain. What is the one requirement in order for a prokaryote to start doing fermentation instead of all the other steps? Absence of oxygen. Because if they have oxygen, they're going to want to do glycolysis, Krebs, and electron transport chain. Because you can make over 10 times more energy per molecule of glucose by going through all those steps. But if you take the oxygen away, they're going to do something for survival. Okay? Fermentation is the process where we use the same step of glycolysis plus one extra step, simply trying to make a little bit of energy to live on. When they do fermentation, the glycolysis step is exactly the same. We take the 6-carbon glucose, split it in half, form 2 molecules of pyruvate. During this step, make a little bit of energy. This is it. That's all the energy they have to live on. So if you're going to run a marathon, you can't do it by fermentation. Okay? When organisms start living that way, they're not growing very fast. They're not doing anything very fast. Mm-hmm. Mm-hmm. Well, they just drew their pictures differently. It forms 2 net. You actually used to, it just didn't show you the numbers in that first picture. It's exactly the same. 2 molecules of ATP, 2 molecules of NADH, both times. Okay? It actually, when you go through glycolysis, you form 4 molecules of ATP, but you use 2. So it's actually just a net of 2. So I don't make y'all, y'all don't have to memorize numbers. Okay? All right? So that's exactly the same. Why do we need this extra step? Because as we go through glycolysis, we use NAD to form NADH. That is just a step that has to happen for glycolysis to occur. We go through the next step so that the NADH will be used, releasing NAD. The NAD can go back up here and be used again. So that second step is simply so we can make what we need to do the first step. The first step is where we make our energy. Second step gets us so we can go back to the first step. Okay? And some of you are like, yeah, that makes sense. Stop saying it. But this is one of those things that some people just have a little harder time accepting. So that's why I say it so many times. Okay? What are examples of things we use fermentation for our own benefit? Making wine, making any type of alcohol, making bread, all that stuff. Okay? You can go buy at Walmart a little package of yeast. Anybody ever bought a package of yeast? Okay? That is a live microorganism. It's just been desiccated, meaning they took the water out of it. Yeast are very hardy little organisms. Okay? So as soon as you put water in them, they swell back up and start living again. And so you've put a live microorganism in your food, and it starts doing this, producing the carbon dioxide, making your bread rise, making your alcohol, any of that good stuff. Okay? You all know what yeast smells like, you just don't know it, because the yeast plants, like not even a mile from here. Have you ever smelled that kind of sweet, kind of weird smell every now and then when you come on campus? That's the yeast plant. So I'll try to point it out next time if y'all help me remember. Once you smell it once, you'll never forget that it's yeast. Okay, so now let's get to where we need to spend a little bit more time today, and that's finishing photosynthesis. We didn't spend as much time on this the other day. Photosynthesis you can think of as almost the exact opposite in many ways of what we just talked about, right? The purpose of the carbohydrate catabolism we just went over was to use sugar to make energy, right? The purpose of photosynthesis is to make sugar. They're making that sugar so they can do all those steps we just talked about. Okay? Photosynthesis occurs in organisms that don't have the ability to go get food like we do. If we need to make energy, we go eat food, and then we break the sugars down into energy. A plant or photosynthetic bacteria can't do that. So they have to use the energy from light to make their own food so they can break it down for energy. Does that make sense? Okay. Why is it incorrect to ever tell me that the purpose of photosynthesis is to make oxygen? It's their just accident byproduct. Oxygen is their waste product. It's selfish and conceited to say that plants make oxygen for us. They don't. We just happen to be able to use it. Okay? So that's a very important distinction. 2 different steps of photosynthesis. We have the light-dependent reaction and the Calvin-Benson cycle. Light-dependent tells us we need what? Light. Got to have light. Okay? The Calvin-Benson cycle is light independent. Doesn't mean it happens in the dark. Just means that series of reactions does not require light. Okay? Now I listed it here for you, but we're fixing to go through it. The purpose of the light-dependent reaction, making some energy. And also, we make this NADPH. We're going to see we use that as well. The purpose of the Calvin-Benson cycle is to make sugar. Okay? So in first set of reactions, we make ATP and NADPH. Guess what we use in the Calvin-Benson cycle? ATP, NADPH. So the first set of reactions, we're going to make what we need to use in the second set of reactions. Does that seem familiar? What did we do in the steps we just talked about, right? Glycolysis, we split it in half so we could use the smaller molecules in the next step. Krebs cycle, we made NADH to use the NADH in the next step. Okay, so same trend. What we make, we're making it so we can use it. Okay? So let's look at our light-dependent reactions. Now, we went over these last time, and we said when we first flipped the slide, looks horrific, right? But it's not that bad. It's much, much simpler than what we've been going over. Two types, cyclic and non-cyclic photophosphorylation. Even the word sounds bad, but we broke it down. What does photo tell us? Uses light. What does phosphorylation mean? Adding a phosphate. The most important reaction where we add phosphates is turning ADP into ATP. That's where that phosphorylation comes in. Cyclic tells us what? Cycle. So you're going to look exactly like you did to begin with once you're done. Everything's going to go through that cycle. Non-cyclic tells us it's going to be a little different. We're not going to go all the way back to the exact same beginning point. Okay? First, let's do cyclic. It's the older version, but it still works for a lot of bacteria. In cyclic, step 1, light comes in and hits the chlorophyll. Where's the chlorophyll? In the chloroplast. If the organism doesn't have a chloroplast, it's just in the cytoplasm. Chlorophyll is a pigment. And I said this last time we had class, and I got thinking about it. It's kind of a wrong thing to say. I asked you, why is the chlorophyll green in this picture? Because it usually is green. That's what makes plants green. But not all chlorophyll is green. That's just plant chlorophyll. So that's just kind of a bad thing to say. For what we usually think of, it's what makes the plant green. All right. So what happens when light hits that chlorophyll? It heats it up, right? And the electrons get excited and start shaking around, right? Once they get excited and start shaking around, what do the electrons do? They start jumping, right? Same thing that happened if it got hot in here. What would we all start doing? We'd all start getting antsy, right? Moving around, trying to cool off. That's what they're doing. They get all excited, shaking around. Once that electron jumps up, it jumps into a protein of the electron transport chain. What happens as electrons jump through the electron transport chain? We pump a what? Proton to the top. When I get a bunch of protons at the top, they flow through the ATPase, start spinning, and we make what? ATP. What makes this cyclic, where does that electron go once it's done? Hops right back into that chlorophyll. That's easy, right? Okay, let's see if you really understand. Let's look at non-cyclic. So you guys are going to lead this discussion. Okay, step 1, light hits the chlorophyll. What happens? Heats up, electrons get excited, electron jumps up. In this one, we have 2 different photosystems. Don't let that bother you. Eventually, where does the electron jump to? Electron transport chain. As the electron starts jumping to the electron transport chain, we pump protons. Once we get enough protons, they flow back through the ATPase. We produce ATP. This is non-cyclic. So does the electron go back to the chlorophyll? No. Electron goes where? NADP. When the electron combines with NADP, we make what? NADPH. This is exactly the way our NAD and NADH works, right? How do we remember that? Why do we put the P in it? because this is photosynthesis. Only time you ever see that NADP is when you're doing photosynthesis. So if you're taking a test and you have no idea what the answer is, and you see NADP, well, you should at least be able to say, okay, well, I know we're talking about photosynthesis now, and, you know, move your answer that direction. Okay? So is that the only thing we need to talk about right here? No, right? Because if we just keep doing just that over and over again, what's going to happen to my chlorophyll? He's going to run out of electrons, right? So we got to put electrons back in that chlorophyll. Where does that plant or that photosynthetic bacteria get its electrons from? Water. The chlorophyll pulls the electron out, and what is made as a waste product from that water? Oxygen. Just like carbon dioxide is our waste product, oxygen is the plant's waste product. Okay? So we feel okay about this? We're ready to see the next step? Some of y'all are looking at me like, no. All right. Here's the next step. Again, you notice this is not a picture from your book. Because, my gosh, I don't know why they make some of these cycles look so complicated. So that's why this is a picture that I just found somewhere, because I thought it made much more sense. So let me tell you what happens, and then we'll go back through and make sure everybody's got it. Okay? So what do we start with in the Calvin-Benson cycle? We start with several molecules of carbon dioxide. That's our substrate. That's what we start with. Where do they get that carbon dioxide from? From us, from the air, right? All the organisms that have released CO2 as a waste product, the photosynthetic organisms just use that. Okay? We said the overall goal of this is to make what? Anybody remember? Sugar. So that's what's down here. This is your product, sugars. And do you remember back at the very beginning, I told you never had to draw chemical structures, right? But I showed you the basic structure of a sugar was this, right? 6 carbons stuck together. So you kind of see what we're doing? We take 6 molecules of CO2. There's our 6 carbons. So the whole thing we're doing in this cycle is we just got to put those 6 carbons together so we can make our sugar. This is simply taking something little and hooking them together, trying to make them big. Unfortunately, it's not as easy as just here they are, poof, they go together. It's several steps to get there. Okay? So here come our CO2s. They come in. We actually need more water, but we're not going to talk about all the chemistry of why. But just see, plants need lots of water. So our CO2 comes in. We go through a whole bunch of steps. Okay? Notice what we're using as we go through the steps. Okay? This is the butt end of the arrow, right? So that means it's going into the reaction. We use ATP and we use NADPH. Where did those molecules come from? The ATP and the NADPH. Where'd they come from? These reactions we just did, right? So those molecules come from the light-dependent reactions. There's no way you'll be able to read this. All right, anyway. From the light-dependent reactions. Okay? So it's really important to me that you understand they got the CO2. It was a waste product from somebody else. They start going through the steps. These steps require using things that the organism just made. As they keep going through the cycle, they will spit out their sugars, glucose, other sugars, but mainly glucose. Okay? And just to make a point, you see they use a whole bunch of ATP again over here. It's a very energetically costly process for them to make a sugar. There has to be a reason that the organisms like us that are higher up the evolutionary tree don't do this, because we use our energy to do things like move around. Plants don't do much walking around, right? So they can use all their energy they make to make their sugar. Okay? So now do you agree with me that photosynthesis is much easier than the other reactions? Right? I don't know why, but students hate photosynthesis. It's really easier. What's your question, Kara? Yeah, and they can happen at the same time. But I guess at some point, the light dependent had to happen first. But they both just continue all the time until the sun goes down, then the light dependent takes a break. Unless you got your plant inside. They can live off of the light from your lights. Well, this sugar, they can do carbohydrate catabolism. They can break the sugar down. It's a little different, but they can break that sugar down to make more energy for when they're growing, producing other things for the plant. The energy made in the light-dependent reactions is used for this. They make the sugar, and then they can break that sugar down to make energy for everything else the plant has to do. Okay? So how do we feel? Some of you are saying good, better, okay? The more you hear them, the more they make sense, okay? This is one time when a lot of times I'll say, I don't know why you guys want to listen to me at home, but this is one time that I really think hearing it over and over again does help. So if you have the ability to listen and you want to, that's why I record it. It's certainly not for myself because I don't listen to them. Okay? So the last thing we're going to do today is go over 4 words. I know this graph or this chart looks bad. You don't have to learn this chart. I just wanted to show you a couple things about it. Okay? Now, we went over those 2 sets of pathways like that is the way it works. Not really. Those are just the 2 most common metabolic pathways. There are lots of weird organisms on Earth that don't do photosynthesis, don't need oxygen. There's lots of ways we can change those reactions. And of course we're not going to learn all of them. It's not a metabolism class. But there's terminology we use to describe what the organism uses in its normal everyday metabolism that I think some of them are kind of worth knowing. Okay? How many of you have ever heard the terminology Chemoheterotroph, Photoautotroph? Heard some of those words. Okay? If I say Chemoheterotroph, most people would say, I know what that is. We are Chemoheterotrophs. Okay, that's true, we are, but you need to know what the word means. Okay, so we're going to break it down into 2 separate things. We can categorize our organisms by how they make their energy. That's the easiest one to start with. How you make your energy categorizes you as a phototroph or a chemotroph. What does photo mean? Light. What does chemo mean? Chemical. So that means all organisms on Earth make their energy one of 2 ways. They either use light to make energy or they use chemicals to make energy. What do you think you are? You're a chemotroph, right? You can't just go stand in the sunlight and energy happen, right? That doesn't make sense. Who is a phototroph? Plants, because they do photosynthesis. They can use light for energy. So that's the easy one, right? The other 2 are a little harder to explain. There's autotrophs and heterotrophs. This terminology tells us where the carbon comes from in the organism's metabolic pathways. Okay? The easiest way to describe the difference is to tell you that an autotroph, auto means self. So an autotroph generally makes its own food. And we just went over photosynthesis, right? The first step in this Calvin-Benson cycle where they're making their own food, what goes in? Carbon dioxide. So 99% of the time, an autotroph uses carbon dioxide to make a sugar. Hetero means what? What does that word mean? It means other. Okay? Hetero meaning other. If you're a heterotroph, you're getting your food from something else. You're not making your own food. By definition, heterotrophs use organic carbon. Organic just means it's composed of carbon, hydrogen, and oxygen. That would be sugars, fats, the things you eat make you a heterotroph. Okay? So the easy ones most people can remember is a chemo, and you put them together, chemoheterotroph. That is you. You eat something, you get your food from somewhere else, you break your food down to make energy. You're a chemoheterotroph. Okay? The other most common one you'll see is a photoautotroph. And that's going to be plants or algae. Your photosynthetic organisms. Those are the ones that are photoautotrophs. The other two, really, really weird. You don't hardly ever see those, so I'm not going to make you memorize them because I don't think you'd ever come in contact with them in your lifetime. Okay? But here's the most important thing, I guess. Do you think you are the only chemoheterotroph? No. When we start talking about all the other eukaryotes, you're going to see that most eukaryotes are chemoheterotrophs. Mushrooms are chemoheterotrophs. What's a mushroom? It's a fungus. Yeast are a fungus. They're chemoheterotrophs. So you don't have to memorize this now. I'm just kind of giving you a preview. Okay? Protozoans, worms, all those other organisms we're going to talk about besides bacteria that infect you are chemoheterotrophs. In other words, a mushroom and a worm is way more like you than it is other things. Okay? A mushroom is much more closely related to you than it is a plant. That's hard to accept, right? But if you sit down and look at their metabolism, their metabolic pathways are much more similar to yours than a plant. So it's just important to have that idea of most of the things that make their own food, they use light for that. They're usually photosynthetic. If they have to eat, they do like us. They make energy the way we do. Some mushrooms make poisonous things that are just poisonous to us. Most mushrooms wouldn't do anything but give you diarrhea. They wouldn't kill you. When they say they'll make you sick, they just like upset your stomach. Some of them make you happy, right? But you know, you have to already be a little crazy because the mushrooms that people eat that are like a illicit drug, y'all know what they grow out of, right? Cow poop. So you already had to be a little crazy to me if you were going to go dig in the poop and eat something. But that's just my personal opinion. I would never eat something out of poo. That's just my personal opinion. I shouldn't say this while I'm recording, but my husband was watching Jackass 2 last night, and I had to leave the room when they paid him money to eat horse poop out of the field. I was like, I can't even watch this anymore. Like I'm too intelligent to watch this TV show. I've decided, and it upsets me that they're millionaires and I'll never be a millionaire. Okay, yeah, I go eat poop and record it. And I can be a millionaire. All right. So anyway. I'm not going to test you in big detail. I just wanted you to kind of know what those words mean. We're going to see them as we go through. Okay, so we always have this slide on here. All right.